Okay, so the plan for today is to talk about applications of network flow. So that includes things you would normally think of as applications, using network flows to solve toy versions of real-life problems, but also more unexpected, I think, applications to mathematics. So let me start with one very genuine application, not so much of flows, but cuts. Okay, so this is a map, an old map from 1955. It shows the western part of Soviet Union and what is called at the time the satellite states, so the socialist post-war states. Right, so this is a map a couple of researchers in US defense agencies were looking at, and the interest was, so we're talking 55, right? So this is the Cold War already. So these researchers were interested not in sending flow in this network, but in cutting this network. So they were interested in minimum cut, kind of to cut the supplies from, Soviet Union to the satellite states in case of the war. Right? So they calculated it to be something of this sort. Okay, so this is there's a very interesting reference here by Alexander Shriver that talks about very early applications of network flows, one that even predate Ford Fulkerson algorithm. So it seems like algorithms for network flows was one of those things that were invented by military before they were rediscovered by, non-military researchers, like much of cryptography. Okay, but yes, I think this establishes that network flows and network cuts are important. Okay, so let's talk about some other applications. So one very obvious application is bipartite matching. Okay, what's bipartite matching? Well, you probably remember the definition of a bipartite graph. A graph is bipartite if it's the joint union of two parts, and each edge goes between the parts. Okay, so that would be an example of a bipartite graph with parts 1 to 5 and 1 prime to 5 prime. So the highlighted edges, so the orange ones in this picture, form a matching. So formally, matching is a collection of edges so that each node appears in at most one edge. Okay, so if you eyeball this matching, this matching has size 3, contains 3 edges. If you eyeball it, it's probably easy to find a larger matching. For instance, you can take all horizontal edges, like all flat edges. So the goal in the bipartite matching problem is, given a bipartite graph, find the maximum cardinality matching. Right, so in this case, you can find this one, the flat one. You can find this other matching of size 4. It takes a little bit more effort to establish that 4 is actually the best you can do. Okay, so it's not immediately obvious why you cannot have a matching of size 5, but okay. So maybe there are ways to argue it, but they're not completely trivial. Okay, so generally, how do you find the maximum matching? How do you establish that the matching you have is indeed maximum? And and why would you want to do bipartite matchings? Okay, so matching, if you have, for instance, if you have students and teachers, for one-on-one classes, right? So then you can ask students maybe teachers which students they can teach because of schedule constraints, right? And the maximum matching is sort of the maximum number of tutorials you can schedule. So what we normally have is, when we schedule students to classes, though, is a more general situation. We have more students than classes. So for instance, we may want to schedule 3 classes of capacity 10 each. So this would be typical for this department. I think for this class we have 2 departmental classes of capacity roughly 10. Okay, so now suppose the class time slots are fixed, right? And students, of course, they have their own time constraints, right? So a student can make class 1 but not class 2 and 3. Someone can make class 3 and 1 but not class 2. Can you capture that by bipartite matching? Well, okay, so it's not exactly 1-to-1, but there's a simple trick. So say these are our students. So let's say now the size of each group is 3. So let me create 3 copies of each class. Right? 3 slots in class 1, 3 slots in class 2, 3 slots in class 3. Right? And let edges denote students' preferences over classes. And by preferences, I mean very simple thing. Can you make this class or not? Right? So for instance, student A can make class 1 but not 2 and 3. So we connect him to all 3 1 nodes on the right. Student F can make classes 2 and 3, so we connect him to those 6 nodes, etc. Right, and now kind of clearly matching in this graph is an assignment of students to classes. A maximum matching is a matching that assigns as many students as possible. Right, so that's a simple application. Okay, other examples, well, workers to tasks. Right, so imagine a large project where each worker may be able to do a subset of tasks. You want to assign one task to each worker. Well, men to women, so imagine running a dating website, say, right, and you want to match your customers somehow. Okay, so perhaps commercially, more importantly, this is a real example, ads to web pages. So your advertisers may have preferences for the kinds of pages on which their ads appear. So for instance, in the context of Google search, so if you advertise for whatever, if you advertise a certain brand of shoes, you may want your ad to be shown whenever a customer searches for running shoes. Right, so then, ads have preferences over pages to be shown on. Right, so again, that's a matching problem. It's bipartite because you have ads and web pages, and plenty of other applications. Okay, so it's important, so how do we solve it? And there's a really neat reduction from bipartite matching to match flow. So here's how we do it. So let's start with our instance of matching. First, okay, so suppose this is our graph for matching. We make it directed by directing edges from left to right. Then we add two additional nodes, a source and a sink. We add edges from the source to the left-hand side and edges from the right-hand side to the sink. Right, and they all sort of flow in the same direction. Right, so we just take our bipartite graph, put little arrows here, direct the edges, and add those vertices with adjacent edges. Okay, so now capacities. So how do we set capacities? Well, we assign one simple thing we can do is to assign unit capacities to all edges. A variant that also works and is useful for some things is to assign infinity capacities to these intermediate edges. So the proof of correctness of the reduction I'm going to show works for both unit capacities and infinite capacities. So what is crucial is that these capacities are set to 1. Right? So those can be 1 or infinity. Right, and you can see that if you actually have a flow in this network, and these capacities are 1, you'll never need to send more than 1 unit of flow here, right? Because there's only 1 unit of flow that can possibly arrive. So basically, anything above 1 would mean the same thing. Okay, so this is the construction. Right, so the only caveat is that instead of this 1, we can have infinity. Okay, so what is the claim now? Well, the claim now is that maximum cardinality of a matching in the graph is exactly the size of the maximum flow. Right, and there are 2 directions to show. So let me see which one I have first. So graphically, the first one is if I have a matching of size k, I have a flow of size k. Right, and that's effectively proved by picture. Right, so if this is my matching, so highlighted with orange edges, then this is my flow. Why is it a valid flow? Okay, so what is the flow? So I'm using exactly the same edges as in the matching. So I'm sending flow to feed those edges and flow from S. Right, and then the flow that comes from these edges has to be sent to D. Okay, so why is it valid? Well, so note that exactly because it's a matching, no node here needs to have more than 1 unit of flow to be sent to it. Right, so we can send the requested amount of flow from S. Right, if it wasn't a matching, we'd be in trouble. Right, if we had 2 edges leaving 3, which would both require 1 unit of flow, we couldn't send enough flow from S. But exactly because it's a matching, we can send enough flow from S, and we almost have enough capacity to send all this flow to T eventually. Okay, so that should be straightforward enough. Okay, the opposite direction is basically the same,